I'm going to hand over to Glenn now for a small section on what's very interesting to give you a connection between the two. I got involved in coal geology. I was in big coal mines, and I was always asking the field geologists, well, if you say these fossil trees in the coal grew here, where's the soil? Right. Now, that was my first research project with permission from the government to go in and do a week's research in this government mine, and yet there was no soil. And the geologist hadn't, you could tell he'd never even thought of that as a question. Now, over the years, I've gone and I've asked many soil experts, how do you recognize a fossil soil? And they said, that's not our problem. That's a geologist's problem. And then I'd go to the geologist and they say, that's not our problem. That's a soil expert's problem.
Yeah, and I find it interesting that these polystrate trees that we find are always embedded down into the coal. And we've seen that swamps don't make coal, they make soil. But that's coal that they're buried in, not soil. So we're going to go to my slides here. And let's see, I think it's this.
By the way, Glenn, before, in case we've got new viewers, tell them what your background is.
My background is soil science, soil physics. And my first love was in pedology, describing the soils and characterizing the soils.
And so where did you do this? Where did you actually do this?
LSU is where my BS and my master's degree were, and that's where I was on soil judging teams, and then PhD at University of Arkansas. So that's what you were asking.
That's what I'm asking. And what university did you work at for much of your life?
University of Tennessee, as well as University of Nevada as well. All right, so as John was talking about the layers, one of the things that the early developers didn't have was the advantage of seeing these processes in action. We watched Mount St. Helens on the TV and saw how it could just rapidly create these layers. And so geologists have gone back to what they originally believed in, catastrophic processes. Many of them have, I guess not all of them, but they insert, as John has showed earlier, this missing time, that there'll be a catastrophic process that'll lay down a layer, but then there's millions of years till the next one. And you can see that here. These are pictures from the Grand Canyon, and between layers, there may be 160 million to 12 million. And we talked previously about, what happens during that time? If there's missing time, is that supported? Is that valid? Is it supported by science? Because things are going to take place. You're going to get plants growing. And if you're getting grasses growing on the surface and they die back each year, you're getting roots growing in the subsurface. That root system grew in 1 year. All of those are depositing organic matter. And so at Mount St. Helens, when it was so devastated, they said, it's going to take hundreds. One scientist said it would take over 1,000 years to get vegetation to come back into that area. It was so buried in sediment. And yet, within just a short time, they had vegetation within just a matter of a few years. And I mentioned before that I went there 16 years later in those deposits, and there was already soil profiles being developed. So what is a soil profile? Well, soil is a living being. It's got to have life for it to be soil. It's got to have a series of layers, starting with the A horizon, which is an accumulation of organic matter, and it's very distinctive. You may have an organic layer at the surface with a lot of leaves, but you're going to develop this A horizon, which is the decomposed organic matter. And that's a distinctive horizon that allows us to be able to recognize soils. And then you get a B layer, which is a weathered layer where there's been some translocation of clays and such, or a removal of the clays. And then you get down to a C horizon, which is down to your parent material that it's supposedly developed from. So what I wanted to talk about was, we've mentioned before, when you look at the layers, whether you're in the Grand Canyon, like this picture we took from our rafting trip a few years ago, or you're driving down the interstate here in Tennessee, you're driving anywhere or watching TV. Just watch the old movies and you'll see everywhere over the world, you see these layers, and they're just one layer stacked on top of the other. And the question is, where are the soils? So we have brought out in the past that, well, that's a good indication that these were laid down all at this very rapidly one time, a layer on top of a layer on top of a layer, and laid down in lateral flowing system. But there is a thing called paleosoils, fossil soils. And this is a field of science that has really grown over the last couple of decades, because they're going in and identifying these fossil soils that then they use to relate to climate change using proxy measurements of the climate. Well, in soil science, we look at paleosoils as identifying buried soil horizons. And I've used this in soils in my research to identify buried soil horizons that give you a little bit of a history. In fact, there was one research project I was working on, and I was finding these buried soils that looked fairly recent. And I went and talked to the landowner. He goes, "Oh, yeah, back when my dad bought this property, I remember him telling me about how, 50 years before he bought the property in the 1930s, he went and tore all the trees down with a bulldozer, burned them, and then scraped all of the material over to this area, filled in all the lower lying areas." I was like, "Oh, okay, well, that's pretty obvious from the buried soils." But what's going on in paleo soils in this field of science is they go in looking for buried soils. The problem is, this is in a review, annual review, Earth Planet Science. They said recognition of horizon boundaries is integral to soil description. Yes, it is. It's integral to classification. Yes, it is. But they say the task is considerably more complicated in paleo soils. A horizon may be difficult to identify and may be entirely or partially removed by erosion. The original soil surface is seldom preserved. And what they go on to talk about is this A horizon, this critical, that distinctive horizon that constitutes a soil, is missing. They don't find those. So they're basing it on other characteristics of what they would call a B horizon. Well, in soil science, my question would be, where's this missing A horizon? Where did it go? Because we see all these layers laid out. Well, if the A horizon, the organic matter, has been stripped off, where did it go to? Because in soils, we see this association, we call it a catena, with a landscape position. I remember in soil judging, we would travel around the state and into other states looking at soils. And we were down in the Cajun area, the French area, and they had a transition of soils from the Grand Coteau to the Jeanneret, the Cajun French towns. Again, John, just like the rock layers are named after towns, the Jura Mountains, we do the same thing in soils. And basically, it was just a slight slope, but you could trace the organic matter accumulation that made this Jeanneret a beautiful organic. We'd call that a mollisoil, very productive, but the upper hill slope positions were not. So where is the soil? They just can't find any soil, but they claim they find old fossil soils. Well, what's that based on? It's based upon other characteristics, changes that they see. And sometimes it will be roots. They will find what they find are roots, such as this one. I don't know if you see my arrow in slide B up there, but the roots aren't attached to anything. So the question is, are they really finding these B horizons? Because there are other processes that can develop voids in the soil that can be filled in with sediment, but it wouldn't be roots. Watch the video. This is from some of my research. As water infiltrates into the soil, it has to displace the air. Well, the air, when you've got a nearly saturated soil, As that water infiltrates, it's got to force the entrapped air out. And what it does is it just makes a void, a vertical path that'll look much like a root channel. Internal erosion, which is what I spent most of my end of my career studying, creates vertical and lateral voids. We call them soil pipes. So the question is, even if you found a buried root, is it an indication of where it grew? We see this all the time, polystrate trees. They're buried there, but they didn't grow there. That's their buried location. And then you have groundwater flow that translocates fines, that moves the fines around. I used to do a lot of work on colloid transport, and you get water movement through the soil. Well, if these materials are laid down by water, there's going to be a redistribution of that water. There's going to be a translocation of fines and even a translocation of the calcium and other minerals in that water. So, my view is, even, where are these soils? Because I don't see these paleo soils, these fossil soils. And the way it seems like to me, a lot of this is used to describe these could very easily be explained by much more obvious processes. And even if their soils are missing the A horizons, how do you still have these abrupt layers, these abrupt distinct layers? Because a bioturbation is going to be mixing those layers up if it's millions of years of time missing. And so my question is, what kind of environment could produce that much sediment that doesn't exhibit any evidence of any biological activity for millions of years? And if you don't have the biological activity, if you don't have the grass, you don't have good cover, you're going to get gullies. John, you may recognize the one on the upper right. That's from Australia when I came to visit you. Some of these others are from China and various places. This is from my research on gully erosion. And of course, then if it's out there and it has no ground cover, you're going to get gullies forming. And then you get another deposition event. Well, it's going to fill those in. And when you look at these layers, you ought to have just many, many, many gullies showing that are in field. But we don't see that. So again, what kind of environment would leave the ground bare but not exhibit any evidence of erosion for millions of years? And I just think this whole idea that sediment can be laid down over this long period of time and have no soil development, no bioturbation, no erosion is just utterly preposterous. I like what these guys with Canyon Ministries, Nate Loper is now the executive director. Bryce Brothers was also one of our guides on our trip. And they said, instead of believing in what's missing, time, soils, bioturbation, erosion, why not base your beliefs on what's observed? Kind of hard to argue with that. So, because I do find evidence of roots. This is filled in roots. This came from a whole stump. I think this was in Nevada. John, you'll recognize this. We find these roots all the time, but they're never associated with a tree. And these are filled in by the sediment, filled in the trace fossils.